Good morning. Yeah, this is Charles.
Good morning, sir. Uh, Sir, can we get your contact number in order to contact you?
Yes, it's Node 774
Okay, sir.
6967
Yes, sir.
95.
Sure, sir. Thank you very much.
Sir, so your audio and video seems to be fine. So can you try sharing your screen as well, for just in case, so to check the before we start the session. Okay, yeah. Okay, great. So I can see the screen as well. Thank you very much, sir.
Okay. So who would be supporting me in this session, the technical and the other aspects? Yasoda and
So yeah, I will be sharing the videos and those things. So technical part. So yeah, Shoda will be doing the basically comparing part before handing over the session for you, sir.
okay, okay.
So you can like continue the session after she hand the session over to you, sir.
Okay, okay, thanks.
Very good morning to all of you. Welcome to session 1B on machine learning. Let me introduce you to this session chair, Dr. Andrew Charles. Dr. Andrew Charles is a graduate from the University of Jaffna, Sri Lanka. He obtained his PhD in systems engineering at the Cardiff School of Engineering, Wales, the United Kingdom in 2007. Dr. Charles joined the Department of Computer Science, the University of Jaffna in 2001, and presently he is serving as a senior lecturer. He has served as the head of the Department of Computer Science and head of Computer Center at University of Jaffna. Presently, he is the director for implementing the World Bank-funded HEAD project at the University of Jaffna. He is actively involved in the administration of the network services and information systems at the University of Jaffna. Dr. Charles has authored over 25 peer-reviewed research papers, and his research interests are in the fields of data mining, machine learning, and natural language processing. He is a recipient of the Sri Lanka President's Award for Research. Dr. Charles, I invite you to lead the session from here onwards. Thank you.
Thank you, Yashoda, for the kind introduction. So, very good morning to you all. So, I welcome you for the ICTER 2021 conference. So, say maybe it's unfortunate or fortunate here. We have to do it online. Otherwise, so it would be a great event meeting you all in person. Anyway, so I welcome all the presenters of research papers to this session and all the audiences to this session. So without further delay, we can start with the first paper. So in this session, we're going to have 5 papers. So each are in different fields and different techniques. So I hope it would be an interesting session. So the first paper, ensemble methods based machine learning approach for weather prediction for precision agriculture. And so this is going to be presented by JSANW Premachandra, so who is following a BSc honors degree in software engineering at the Faculty of Computing of General Sri John Kotlawala Defence University. And currently she is doing her internship at the IFS R&D Private Limited as a software engineer. So she is interested in mobile application development, machine learning, and agile development. So over to the presenter.
Hello everyone, I'm Nishadi Premachandra presenting our research Ensemble Methods-Based Machine Learning Approach for Weather Prediction for Precision Agriculture. The co-authors of this research are MD PP Gunatilaka and our research supervisor is Mr. PPN Kumara. We are from the Department of Computer Science, General Sir John Kotlawala Defence University. This presentation will include these areas, so let's move on. As an introduction, climatic variability in recent years has critically affected the usual aspects of human lives, where the agriculture sector can be considered as one of the most vulnerable. The mismatch between the rainfall pattern and traditional seasonal cultivation schedules has adversely affected the agricultural sustainability. Even with the current technological advancements, weather prediction is one of the most technically and scientifically challenging tasks. As a developing country in the Asian region, Sri Lanka has an economy based on agriculture, while emphasizing that the agriculture sector is playing a significant role in the country's current development in both economic and social aspects. According to the report Sustainable Sri Lanka 2030 Vision and Strategic Path, as a developing country, Sri Lanka is facing potential agricultural risks due to unpredictable climatic changes. These climatic changes have been resulted in rainfall pattern changes where the expected rain may not occur during the expected time as well as with the expected amount and intensity. As a result, a mismatch between the rainfall pattern and traditional seasonal cultivation schedule will happen. This problem indicates the current necessity of an advanced weather prediction model that can be used to guide farmers on their cultivation schedules based on weather and make them ready to handle the issues that occur with the uncertain climatic changes. So, accurate weather forecasts enable farmers to schedule their cultivation tasks while minimizing weather-based agricultural damages. Therefore, the aim of this research is to introduce an ensemble methods-based machine learning approach for weather prediction for precision agriculture. So, identifying and analyzing the existing solutions and technologies is a significant objective in our research, and for that, we have conducted a comprehensive literature review. So, this is a summary on the most remarkable approaches based on different techniques, including neural networks, regression, random forest, and ensemble methods, etc. As you can see, in addition to the technologies used, we have analyzed these applications based on their accuracies, benefits, and drawbacks as well. All these research works have conducted in different countries based on the relevant geographical context. Several limitations exist in the currently available weather prediction approaches. Among them, the problems that occur during the data collection process can be identified as a major issue. In addition, inaccuracy in data where the collected data are not related to the problem domain, a high amount of missing data have affected the accuracy of the existing systems. As well, inefficient data preprocessing has also affected the accuracy reductions in current weather prediction systems. As a result of not carefully handling the incomplete and inconsistent data, most systems have been unable to obtain a high quality output. In this literature review, we have recognized that when a prediction model is based on one machine learning algorithm, it has been difficult to select the most appropriate. Even when selecting multiple algorithms, many studies have not been used proper selection criteria. Also, with the reviewed research works, it has been clearly recognized that there is an effectiveness of using ensemble method-based machine learning approaches for weather prediction. So, the proposed architecture of the weather prediction model comprises a set of interrelated steps such as data collection, data preprocessing, exploratory data analysis, model training and testing with the machine learning algorithms as well using ensemble methods, and perform model evaluations. As the first step, an hourly weather data set of 26 months has been collected from the Central Environmental Authority, and it includes 7 weather attributes as rain gauge, wind direction, wind speed, relative humidity, average temperature, solar radiation, and ozone concentration. The original dataset has been improved by generating daily weather records through averaging. In order to ensure the quality of the predicted results, a well-managed set of data preprocessing methods has been selected based on the nature of the dataset. Collected data were clearly analyzed and integrated to a single table under data consolidation. For data reduction, redundant data that might reduce the system performance were removed from the dataset. Under data cleansing, null values were replaced by averaging without just putting zeros. For identifying the dataset features such as normal distribution, correlations, etc., correlation matrices and distribution graphs were used. Through the correlation matrices, the relativity among the weather parameters were computed. According to the results of the exploratory data analysis, correlations among rain gauge and other weather parameters are slightly weak. We have computed correlations between rain gauge and multiple weather parameters, and the correlation between rain gauge and the combination of average temperature, relative humidity, solar radiation, wind direction, wind speed, and ozone concentration is 0.4949, which is a considerably value, considerably high value compared to the correlations obtained by the existing approaches. As the initial step of model training and testing, 4 machine learning algorithms were used, including support vector machine, k-nearest neighbors, random forest, and decision trees. Support vector machine model was chosen as it supports nonlinear features and it achieved an accuracy of 88.32%. Random forest model chosen as it has a simplified methodology to measure the relative importance of every feature on prediction, and it has been achieved an accuracy of 89.18%. The k-nearest neighbor model achieved an accuracy of 89.26%. Decision tree is a supervised machine learning model which is mostly adopted with the categorical data. In this research, decision tree model achieved an accuracy of 89.50%. So in this research, we were able to predict rainfall using machine learning techniques with a considerably high accuracy level, even with a limited data set, but through identifying the most appropriate and related weather parameters and proper data preprocessing techniques. In ensemble methods, multiple models are created and combined to perform the predictive approach. Ensemble methods have been distributed among a wide range, starting from the basic methods up to advanced methods. From the available ensemble methods, only the relevant ensemble methods are elected to compute the results. So here, the averaging method mainly adapted for regression-based scenarios to calculate the average of all prediction models. When evaluating the averaging method, it has achieved a score of 0.9148 mean. Voting-based method adapted with rainfall, support vector machine, and decision tree models. When evaluating the voting method, it has been achieved a score of 0.8858 mean. Bagging is a bootstrapping method which only adopted one base model. Here, bag decision tree selected to compute the mean. When evaluating the bagging method, it has been achieved a score of 0.8936 for mean. Several boosting models are adapted to perform in the boosting method. Here, AdaBoost and AdaBoost with decision tree approach selected to compute the mean. When evaluating the boosting method, it has been achieved a score of 0.9412 for mean. So in this research, we emphasize that the weather is a critical factor in agricultural sustainability perspective. Sri Lanka is also facing difficulties in identifying the mismatch between current rainfall and traditional seasonal cultivation schedules. The proposed architecture attempts to introduce an ensemble methods-based machine learning approach for weather prediction for precision agriculture in Sri Lankan domain. First, it has been concluded that several weather features are applicable for weather prediction in Sri Lanka. The selected features are rain gauge, wind speed, wind direction, humidity, temperature, where solar radiation and ozone concentration are unique features for Sri Lankan context. Secondly, it has been concluded that data preprocessing techniques should be selected by considering the nature of the input data set. In this study, a well-managed set of data preprocessing methods has been selected based on the nature of the dataset in order to enhance the quality level of the final output taken from the prediction process. Thirdly, several machine learning algorithms such as support vector machine, random forest, k-nearest neighbors, and decision tree, as well ensemble methods such as averaging, voting, pegging, and boosting are adapted to explore the results. Finally, from the machine learning algorithms which were identified, decision tree as the best fitted model as it provides the highest accuracy of 89.50% when compared to the other evaluated machine learning algorithms. And from the ensemble methods, boosting method, which includes ADA boost with decision tree approach, has been identified as the best method with the highest accuracy score of 94%, 12%. As for the future work, it is expected to apply machine learning algorithms with a large dataset and more pre-processing techniques like feature engineering. Also, it is expected to apply deep learning for predicting weather and evaluate the accuracy improvement. So we have come to the end of our presentation. And finally, I would like to express our gratitude for everyone who has supported us in this research work. And also, I would like to express my special thanks to ICTER 2021 for offering us with this remarkable opportunity. And yes, thank you very much.
Thank you, Ms. Pramachandra, so for this presentation. So now this work is open for discussion. Okay, so you said you have collected the data from the meteorological department, right?
So we have collected data from the Central Environmental Authority.
Okay. So this data is for a region or it's for the whole Sri Lanka?
So actually, we collected the data set for the 2 years 2 years range for the Kandy district.
Okay. So what do you think, say, if this would fit, say, you have collected it from the Kandy region. So if we give data from Puttalam or if we give data from Mullaitivu, will this model work fine?
So in that case, since we have select algorithms like KNN, decision trees, etc., we believe that they can fit with different data sets without a huge change in terms of accuracy.
Okay. So I would like to ask, in the title, you said precision agriculture, right?
Yes.
In what aspect your work tally with this precision agriculture?
So actually, we have conducted this research as a part of my final year research project. So for that, currently I am working with developing a mobile application for facilitate the paddy cultivation process in Sri Lanka. In that case, I am going to introduce a feature to that mobile application as a weather forecasting. That means when a farmer is going to perform a specific task in cultivation, suppose as an example harvesting. So for that, I'm going to give a weekly weather forecast. That means whether a day will be rainy or unrainy. For the harvesting process, then they can, with the weather forecast, they can select the most appropriate date within the week to perform the task. For that is why I have included the precision agriculture.
Yeah, but okay. So it's yeah, it will give some efficiency, some more planned activities for the particular week, but you need to think of long range also, right? Say in case of paddy, right? They have to decide so which type of crop they're going to harvest. So based on the rainfall, right, or other features. So if the rainfall is going to low, they can use a type of paddy which can withstand low rainfall. Yeah, something like that.
Yes.
Okay. Any other questions from the audience? So it seems I'm the only one tasked with asking questions, right? Okay, one more question I have. So generally speaking, SVM considered to be a superior classifier, right? But in your case, say SVM performed lower, say slightly lower than even KNN, right? So KNN is this slide say it's kind of an averaging. So what do you think, say, what could be the reason for that? Is it the data or the model, or what do you feel?
So as I think it's because of the since during our exploratory data analysis process we recognize that there is since we are working with weather data, there is a non-linearity nature in the data set. So as I think the KNN supports more than support vector machine for non-linearity type data. That's why there's a slight drop in the accuracy in SV.
KNN for nonlinear?
As what I got from the literature review, that most of the researchers have mentioned that they have been able to achieve high accuracy with KNN due to the even with nonlinear data sets.
Okay, yeah. Okay, thanks. Thanks for your presentation and the answering the questions.
Thank you, sir.
Yeah. So in case we don't have any other questions, we can move to the next paper. Yashoda, shall I move to the paper number 36?
Sir, we will be moving on shortly, sir. Shall we wait for 4-5 minutes, sir?
Okay. Or we can go for the paper number 36.
Author of paper 36, is that fine for you to present now?
Yeah.
Sure. In that case, we can move on, sir.
Okay. Yeah, okay. The next paper in this session is, so it's an interesting one, human gut microbiome data analysis for disease likelihood prediction using photo encoders. So this is going to be presented by Diniti Nisana Vikramaratna. She has received her BSc Honors in Computer Science from the University of Colombo School of Computing in 2021. So currently, she is working as a research assistant at the Bioinformatics and Computational Biology Lab, University of Colombo School of Computing. And her research interests include microbiome, workflows, and drug discovery. So microbiome is a less understood area in human let's say physiology. So I welcome Ms. Diniti to present her work.
Everyone, my name is Diniti, and today I will be presenting to you my research, human gut microbiome data analysis for disease likelihood prediction using autoencoders. So first, I'd like to walk you through some concepts that will help you to understand my research better. So starting off with microbes and microbiome, a microbe is a tiny living organism like bacteria, virus, fungus, or protozoa. And the microbiome is the collection of such community of microbes. So if you go to the human microbiome is the composition of all microbes that reside on or within human tissues. So they reside in various body sites like skin, lungs, saliva, and gastrointestinal tract. So if we go to the gut microbiome consists of the microorganisms that live in the gastrointestinal tract. So a majority of bacteria of the human body are housed in this GI tract, and that's about 99% of your entire microbiome, and about 500 to 1,000 species of bacteria reside in the gut. So researchers have found that the gut microbiome is linked to diseases like colorectal cancer, liver cirrhosis, Crohn's disease, ulcerative colitis, obesity, and type 2 diabetes. And the gut microbiomes of diseased individuals tend to have different bacteria species than healthy individuals. So a common alteration is the loss of microbial richness, or we call this a dysbiosis. So moving on to the research problem, gut microbiota and other microbial communities that live in soil and marine environments are complex in terms of alpha diversity. So, alpha diversity is the number of species that live in a single sample. So, if you take the gut, there's thousands of species, and if you take soil, there's about millions of species living in soil. Therefore, microbiome data are high dimensional. So in supervised learning, when you have a high ratio of feature space dimensionality over the dataset, that can cause overfitting. So therefore, we should find suitable methods that can be taken to select features which can give you meaningful interpretations. So two common approaches used for feature selection in microbiome data are lowering the feature resolution below the common 97% sequence identity, and the other one is disregarding species appearing only in few samples or below a certain threshold. So this can cause a loss of important information and therefore are not suitable for microbiota representations. So if you look at the approaches that have been taken for dimensionality reduction in microbiome data, that's mainly feature selection approaches and feature extraction approaches. So in feature selection, you select a subset of features from the original feature set without altering the original representation of the features. So filter methods, embedded methods, wrapper methods are such feature selection approaches. So in features extraction, you transform the data from a higher dimensional space to a lower dimensional space. Autoencoders, principal component analysis, and TSD embeddings are such approaches used in feature extractions. So the research aim is to minimize information loss in traditional approaches of feature reduction that are used for microbiome data analysis. So now let's move on to the research design. So in the research design, the first phase is the data collection phase, and after that the pre-processing phase, followed by feature extraction, and finally using the classifiers to predict disease likelihood prediction. So the first phase of data collection, here species level profiles derived from whole genome sequencing data of previous researchers were used, and these individual datasets will have both diseased and healthy samples. So this is a description of the datasets that were used. The diseases selected were inflammatory bowel disease, type 2 diabetes in Chinese and European women, obesity, liver cirrhosis, and colorectal cancer. And these are the number of samples, healthy controls, number of patient samples, and the number of OTUs, or the number of features in each of these datasets. And the next step is the data pre-processing step. So in this research, two kinds of data sets were used. One is the ones that I mentioned before, and then another experiment was performed after merging some datasets of the previously mentioned datasets. So the datasets selected for the merging were cirrhosis, obesity, and type 2 diabetes. And these are the number of patient samples in each of these datasets and the number of features in each of these merged datasets. Then dimension reduction was performed. So for dimensional reduction, we used autoencoders, the shallow autoencoder and the deep autoencoder. So in shallow autoencoder, there's an input and output layer which is fully connected to the latent layer, which is a lower dimensional representation. A linear activation function was introduced to the latent and output layer. Binary cross entropy was used for the loss function. And four architectures were attempted: SAE 300, 200, 100, and 50. So these numbers refer to the number of nodes in the latent layer. The next one was the deep autoencoders. So in deep autoencoders, you introduce hidden layers between the input and the latent and the output layers, ReLU activation function, and the binary cross entropy function was used for the loss function. Here also 4 architectures were attempted. 2 architectures had 50 nodes in the latent layer and another 2 had 100 nodes in the latent layer. And the encoder and the decoder layers were as mentioned in this table. And then in order to perform classification, after you obtain the low dimensional representation, 3 classifiers were used: the support vector machine, random forest classifier, and deep neural network. So for each of these classifiers, the hyperparameter settings of each of these classifiers were also altered. Then let's move on to the evaluation and results. So for the evaluation, first the dataset was split into training and test data. 80% of the data for the training and 10% to test data. Then after obtaining the low dimensional representation, 5-fold cross-validation was performed on the training set and obtained the best hyperparameters for the classifiers. And finally, testing on the test data. As I mentioned before, there were 2 kinds of experiments used: single disease datasets and multiple disease datasets. So single disease datasets have 2 classes, that are the disease and the control samples. In multiple disease datasets, you have only disease samples. So let's move on to the results of the single disease datasets. So here, this table shows the results obtained for the shallow autoencoders in single disease datasets in terms of AUC. And these values marked in bold red are the best performances for each of these datasets. So for IBD, 0.89 was the best performance in terms of AUC. For EWT2D, 0.79, CT2D, 0.77, obesity, 0.72, cirrhosis 0.87, and colorectal cancer 0.86. So in terms of the classifier, the SVM and DNN have recorded the best AUC in a majority of instances. And then a comparison was performed, selecting the best performances for each of these architectures and each of the datasets. And an architecture that always performs the best was not found. Then moving on to deep autoencoders. So these numbers represent the architecture of the autoencoder. So the first one is having 50 nodes in the latent layer and 200 and 100 node layers between the input and the latent and the output. So in this IBD dataset, 0.92 was the AUC score, that the best AUC score for that dataset. EWT2D 0.7, CT2D 0.79, obesity 0.71, cirrhosis 0.88, colorectal 0.88. Here also, DNN has performed best in a majority of instances. Then after comparison of the deep autoencoders using their best performance in terms of AUC, we could find that 300, 150, 50 architecture gave the best performance in a majority of instances. And then a comparison was made between these 2 autoencoders, SAE and DAE, considering the best performance for each dataset, and we could see that DAE has performed best in majority except for this obesity dataset and EWT2 dataset. Then moving on to the multiple disease datasets. So here also the best performances are shown in bold red: 0.99 for CT2D plus obesity, CT2D plus cirrhosis 0.92, cirrhosis plus obesity 0.99, and for the dataset with all 0.95. Here what's noteworthy to be mentioned is there's a considerable improvement in the performance. For example, the lowest AUC score for datasets with obesity in the single disease datasets was the highest one was AUC of 0.72, whereas here the lowest score for obesity datasets was 0.91. Then after a comparison of the shallow autoencoders, we could not find a single autoencoder that always performs best, but all autoencoders have performed equally well. Then moving on to the deep autoencoders, here also we can see an improved performance compared to the single disease datasets. So the best performance for CT2D plus obesity was 0.98, here 0.93, 0.99, and for all 3, 0.97. So the lowest AUC for a data set with obesity in the multiple disease datasets was 0.9. But the highest recorded for the single disease datasets with obesity was only 0.71. So after the comparison of the deep autoencoders in multiple disease datasets, we could find that this architecture was what performed best in a majority of instances except for this dataset. And after comparing the shallow autoencoder and deep autoencoder, we could find that DAE has performed better than SAE. So we could say that DAE is a better approach for feature extraction in multiple disease datasets. So in order to identify the reasons behind this improved performance in multiple disease datasets compared to the single disease datasets, I performed a visualization using PCA. So in these graphs, these are the single disease datasets. The groups are the healthy samples and the disease samples. So here we can't see a clear separation of the two groups, more like they're overlapping on each other. But in multiple disease datasets, we can see that the groups can be clearly separated, although they don't have clear clusters, they can be clearly separated. So this could contribute to the improved performance in multiple disease datasets. And moving on to the conclusion, so we use shallow autoencoders and deep autoencoders for feature extraction, and in both the single disease and multiple disease datasets, deep autoencoders perform best for a majority of instances. And for classifiers, we use random forest classifier, support vector machine, and deep neural network. And DNN perform best for both multiple and single disease datasets in most instances. And then if we compare the single disease prediction with multi-disease predictions, multiple disease datasets show better performance than single disease datasets. For example, in multiple disease datasets, for the shallow autoencoder, the best AUC was 0.9975, whereas in single datasets, the best was 0.8941, and the lowest for SAE in multiple disease datasets was 0.8664, and the lowest for single disease datasets was AUC score of 0.5219, and the same goes for DAE of multiple disease and single disease datasets. So moving on to the future work, we can improve this study further by improving this multi-class classifier. We can either increase the number of diseases or the size of the dataset. And instead of the species level abundance profiles, we can use strain level profiles. And also we could use different classifiers instead of the ones that were used in this research. So that brings my presentation to an end. Thank you for listening.
Thank you, Diniti, for presenting your work. Now it is open for discussion. So this seems to be a lecture, I'd say. Nobody's asking any questions. Okay. So, Diniti, say, I would like to know more about the data sets. You haven't specified much about the data set, except the names of the data set. So, yeah, if you tell us about the dimensionality and what are the features inside, then we can understand more about this problem with the data set.
Yeah, so the dimensions were mentioned in the table. So they varied like about 200 to 500 range. And
Yes.
the dimensions
Can you
were,
go on? Oh, yeah,
sorry.
go on. Yeah, go on.
Yeah. So, and the dimensions in the dataset are species. So in each of these samples, in each of the patient or the control.
Sample means the quantity. Oh.
No, in that person. So there's healthy people and diseased people.
Yes.
So for each individual, you find the constituent bacteria or the species in the gut microbiome.
Yeah, so whether it's present or not, or it's the concentration of the bacteria.
It's the relative abundance. So like you're kind of calculating a percentage.
Okay.
Yeah.
So, here you have used the autoencoders for the reducing the dimension, right?
Yes. Yeah.
Okay. And say, then for the classifier, you need the label. Say, how did you pass the label to the autoencoders? Or you did something else?
I'm not sure. Follow. Can you repeat the question?
Yeah, autoencoders you have used to reduce the
Dimensions. Yeah.
dimension, but
Yes.
say, so it would be encode the input data, right? Into a
Yes.
flow.
Low
So,
dimension. Yeah.
yeah, so how you pass the labels of the data? So for classification, you need the label, right?
Yes. So that was like separately. After getting the representation or dimension reduced representation, then I use that for the classifier.
Okay, so then you have encoded healthy people separately and
Yeah.
yeah, okay. So in say you, so you said say the multiple disease means a person with multiple disorders, right? So
Not a person. The dataset has multiple diseases. So
okay,
not
okay,
the
yeah.
same person. Yeah.
So the first data set is for a single disease.
Sorry?
Yeah, you have experimented two, right?
Yes. One with single disease and a single, like a disease and a healthy people. And the other one with disease, several diseases.
Okay, yeah. Okay, thanks, Lindsay. Any other questions? Okay, so in that case, thanks, Lindsay, for this informative presentation and good luck in the future.
Thank you.
And we can move to the next one.
Sure, sir. We can move on to paper ID 97, sir.
Okay. So the next paper is machine learning approach for predicting career suitability, career progression, and attrition of IT graduates. So this is going to be presented by two persons. One is Mr. BMD Barnaka, is an undergraduate at Sri Lanka Institute of Information Technology. And he's following a BSc honors degree in information technology, specializing in information technology. And the second presenter, Mr. Dhanasekara. So he's an undergraduate at Sri Lanka Institute of Information Technology and following the same degree as Mr. Barnaka. Okay, over to the Barnaka and Dhaneshkar.
Answers in ICT for emerging regions. Hello, sir, madam. We are honored to participate in the 21st International Conference on Advances in ICT for Emerging Regions. We are the presenters of paper ID 97, titled Machine Learning Approach for Predicting Career Suitability, Career Progression, and Attrition of IT Graduates. These are the author details of our paper. This is the list of contents of my presentation today. First, let's start with the introduction. At present, Sri Lankan IT industry is gaining more popularity among the prevailing industries by attracting young individuals, talents, and professionals in it. Therefore, this can be confirmed based on certain statistics. As per the University Grants Commission in Sri Lanka, in the year of 2019, 12,510 undergraduates have enrolled into the state universities to follow IT-related programs. So it was also stated that there are around 146,089 employees existing in the Sri Lankan IT industry in the year of 2019, according to a survey which was conducted by Information and Communication Technology Agency. Therefore, it can be concluded that there is a massive workforce attached to the Sri Lankan IT industry. So, in order to assist these employees, we have come up with a career mentoring system. Now, this has the ability which it enables. This enables to achieve career suitability predictions for the IT undergraduates, and also career progression predictions for the employees in the software engineering fields, as well as it assists to obtain predictions regarding the employee attrition. Now let us consider the problem areas in this study. Most of the IT undergraduates are unaware of the suitable role for them based on their skills and expertise. This may cause them to change their career at the latter stages of their career life. Inability of an employee in the field of software engineering to determine his career progression, simply the number of years that he or she will be in each career stage based on his professional skills and behaviors, which causes them to be more frustrated as well as lack of work performance. Further, unawareness of the salary range enhancements along with the career progression also causes them to be demotivated. And some employees are unable in identifying their lacking professional skills, which retard their career progression. And also, most of the organizations need to incur a lot of money and time to train new employees for the replacement of the employee attrition. Further, the employees are unaware of the steps to be taken in order to retain their employees within the organization for a longer period of time. Next, let us consider about the research gap of our study. Existing researchers has provided limited assistance to IT graduates to improve themselves for better career opportunities. Also, the existing solutions provide insufficient recommendations regarding the professional courses to be developed by the employees in the field of software engineering in order to have a rapid career progression and to achieve their career goals. Further, less focus was given on the suggestion of remedial actions to retain IT employees within the organization for a longer period of time. Therefore, this implemented solution, career mentoring system, can be used as an all-in-one solution. When considering the research objectives of our study, prediction of initial career and salary for IT undergraduate students, prediction of career and salary range progression, and along with the professional courses prediction in order to speed up the career progression of employees in the software engineering field, and also prediction of IT employee attrition, retention period, and suggestion of remedial action. Moving on to the methodology of our study. Initially, 2 survey questionnaires were designed with the intention of collecting data. One survey was designed for career suitability and progression prediction, which includes 26 questions, while the other survey for employee attrition was designed, which comprised of around 16 questions. Then, These were published among the existing IT employees in the IT industry, in the Sri Lankan IT industry, according to the random sampling method. Next, these collected data was pre-processed. So in order to get rid of null values, invalid and unwanted data. Here methods such as one-hot encoding and standard scaler were practiced. In one-hot encoding method, which it was applied to convert the categorical values in the data into a numerical format, while the standard scaler was used to scale the data. Then the pre-processed data was split as the training set, which comprised around 80% of the data set, and testing data set, which consists of 20% of the data set. Then these were the features and the labels that were considered for the prediction of initial career and the salary range for the IT undergraduate students. The labels are also displayed here. And these were the features that were considered for the prediction of career and salary range progression, along with the professional courses prediction in order to speed up the career progression of an employee in the field of software engineering. And these were the features and the labels that were considered for the prediction of IT employee attrition, retention period, and suggestion of remedial actions. So as shown in the table, several supervised machine learning classification algorithms were used to select the most appropriate algorithm. When considering the career and the salary range progression along with the professional courses recommendation, multi-output classifiers were utilized here. Then, after training the model, evaluation was a significant step in order to arrive at a conclusion about the performance of the model trained. So, considered evaluation metrics include classification reports, confusion matrices, ROC curves, and line. Finally, the REST API was created by using Flask, and the models were deployed in the Heroku Cloud platform.
When it comes to the result analysis of a study, first of all, I would like to explain the result analysis of the prediction of initial career and salary. As shown, among the considered algorithm, XGBoost algorithm provided the highest accuracy for initial career and initial salary range prediction. Next, I move on to the career progression prediction. Here, multiple classification algorithm were utilized. As shown, XGBoost resulted with highest text in accuracy. In here, there are 5 labels such as associate software engineer number of years, software engineer number of years, and so on. When it comes to the prediction of salary range progression, here XGBoost resulted with the highest accuracy. Considered label for the prediction include below 25,000, 25,000, 50,000, so on. Then for the prediction of professional courses to speed up career progression, random forest provided with the highest test in accuracy among the considered algorithm as shown here. Then when it's come to the prediction of employee attrition, random forest provided with the highest test in accuracy. Also, XGBoost classifier provided highest accuracy for the prediction of employee retention period and remedial action. Next, I move on to the evaluation of our models. First evaluation metric I considered is classification report. Here, precision, recall, and F1 score considered for the evaluation. For example, classification report for model performance for initial career prediction is shown here. Since there are 3 classes here, one of all approach is considered. However, all the 3 classes have good F1 score over 0.85, which shows that this model has a good performance. Second evaluation metric I use is confusion matrix. It is used to conceptualize the performance for each classification model on test data. For example, one of the confusion matrix obtained is displayed for career prediction. It can be seen as there is a strong diagonal is obtained. Next, I'm going to mention my third evaluation method, which is the ROC curve. This denotes the true positive rates against false positive rate. One of the ROC curve obtained is shown here. It can be concluded that model has excellent performance in its smooth left corner. Then line was used to identify the features that are having a positive and negative influence on the prediction. This is the system diagram. The main axis actors of the system are the students, employees, and employers. They interact with the web application through the devices. Front-end was implemented using React, back-end was implemented using Node.js, Express framework. Also, the database use Mongoose here. The machine learning models were trained and deployed on the Hadoop cloud platform. Then, when considering the technology stack of the application, we implemented the web application. We use MERN stack, and in machine learning part we use Python, and machine learning model developing we use Hadoop, like these things. And finally, when concluding our study, it can be stated that the system will assist in predicting initial career based on the skill of IT undergraduates and assist in achieving rapid career progression for IT employees in software engineering field by suggesting professional courses, and also for employees to manage the retention of IT employees by suggesting remedial actions. Based on this study, XGBoost algorithm is more suitable for initial career and salary range, and career progression and salary range progression, and employee retention and suggestion remedies. And random forest is more suitable for professional courses recommendation and employee attrition prediction. Further, based on the result analysis, high impact features for the prediction outcomes are determined. As future work, we are trying to enhance our research by collecting more data from several IT organizations with the intention of obtaining higher accuracies, improve the accuracy of the models using parameter and Turing methods, investigate other possible alternative technologies such as convolutional neural networks, and investigate the applicability of career progression and suitability in other fields rather than in the field of software engineering. These are the differences of our study. Thank you.
Thank you, Ms. Banaka and Mr. Danesh Karab. So now it is open for discussion. Yeah, I'm sorry, Banaka, Mr. Banaka.
Yes, sir. Yes, sir.
So I have only the last name, so okay. So I have a small question. Say, you should have considered the social and emotional skills in your questionnaire, right?
Yes, sir.
So what kind of questions are targeted to collect the social emotional skills?
We conduct our survey from the IT professionals in the industry, and
yes.
We got a result from several IT companies and like these things, and these features are considered in data collection.
No. My question is, can you give some example questions which collected social emotional skills?
When it comes to for the employee attrition prediction, we have created a different survey in that, and there we have considered the employee's background and what affects their retention period, whether he is satisfied in his current job position, likewise things also we have considered.
Okay. So in most cases, it's going to be a categorical data, right?
Yeah. Yes.
So how did you model it into your learning methods, learning models?
And then categorical data in data processing part, we use one-hot encoding method. In one-hot encoding method, we can what is male and female, then 2 columns. There is 1 0, and like these things we use one-hot encoding method as a technicality of the data processing. Okay.
So and the models are predicting what they are predicting. Say one is, say, if a person gives the answer the questionnaire, then you suggest.
Firstly, first model suggests what is the most suitable initial careers, like software engineer, business analyst, or salary provision and salary range, and then second component.
There are two things, right? One is the career and the salary.
Salary range.
How fit these two into a single model?
No, there is 2 models for career prediction and salary prediction, salary range prediction. 2 models.
Okay. Okay. And yeah. So any other questions from the audience? I have one more question, but
yeah, I think
how many?
Sorry.
Yes. No, you go ahead. You go ahead.
Okay. It's Chamindra Singh. Just to, in terms of data, you have collected the parameters, the labels that you have collected. For example, the salary. I'm just thinking because I'm in industry. It depends, even if you're a UI or UX or a software engineer, that you have got the data right. But in terms of how much salary within that spectrum, there can be a software engineer with 4 years experience with a spectrum of 100,000, even based on the person's performance. His performance, or that means how good he is in terms of performance evaluation, is it captured, or it's kind of you have taken that as yeah.
Yes, sir. We have captured based on the performance of the employee and based on the company size. Likewise, things have been also considered, sir.
Okay, the performance, let's say performance review, let's say the percentage of, let's say person is 95%, in terms of percentile of performance grading. Is that an input to your categorical data, or is it still not considered in your classifications?
I think you didn't consider, you got this from directly from the employees. So you have to get that from the employer.
In the case of prediction of career progression related, we got the data set from the employees.
In terms of, I'm not, let's say, criticizing your technique. You have done a, let's say, good job of, taking to the technique. But in terms of data, and if you give the meaning to it, there's a total difference in terms of the same batch, same, let's say, experienced person getting two different salaries in the industry based on their performance, how good they are, how good they have progressed. The other one is, I think you have, if I'm not mistaken, you have taken decision trees as the most accurate, but have you considered combining, like pipelining these classifications and getting a better outcome? There's an area of pipelining different classification algorithms and getting a better outcome.
Yes, we use machine learning pipeline, and most of we got high accuracy for the XGBoost classifier and random forest classifier. Most accuracies, highest accuracies we obtain, and we use SVM, decision tree, and KNN like these algorithms, and the best accuracies from XGBoost and random forest.
Okay.
So
I'm okay.
So you did an instance survey. I think this should be, I go through some of the papers, they did, did for maybe 48 months or maybe for a longer period, and getting the feedback from the collected data from the same person for different time slot, that will actually give better results, because rather than getting from arbitrary employees, you have to follow the same employees, how he progress with his career, with his experience and service and all these things. So some of the work they have collected series of to the series of questionnaire from the same person several times.
Okay, so we are the final year in project, and we conduct this survey for the 6 months period of time. We have not time to conduct a large survey like this, because we have to complete on the deadline this project.
So you work with the local data sets. Can we generalize for the other nations or other places the same one?
Sri Lankan context.
This is only for Sri Lankan context.
Yes.
Yeah, thank you, Aruna. So I would like to point out one more thing. Say, you have pointed out the problem in the Sri Lankan IT sector, right? So
Yes,
people are not in the right career, they are not getting the right salary. But you have collected the data from the same set of people, right?
Yeah.
So that has an issue, right? So we have collected data from the people who are not in the right career and the right salary, maybe, right? So in future, you have to think of that. So how you can make the data set more accurate, or say, yeah, of course, we can't have a data set 100% accurate, right? There would be cases, and we should have cases where the number of people or the number of data points are from the right person, so who are in the right career, getting the right salary. Okay, anyway, you good job. Yeah. So you have selected the data the questions what to collect. So it's based from several research papers. That's great. Okay, thank you. And,
Thank you very much.
Thank you, sir.
And we can move to the next one. So any other questions? Okay, then we'll move to the next one. So the next one is paper number 102. Minimize traffic congestion with emergency facilitation using deep reinforcement learning. So this is going to be presented by Dulmina Renuka Kodagoda. So she has received a BSc Honours in Computer Science from University of Colombo School of Computing. So over to Dulmina.
Hello everyone, hope you are doing well. So in this research paper, we are going to present deep reinforcement learning approach to minimize traffic congestion with emergency facilitation. So these are the authors of this paper, Mr. Dulmina Renuka, Ms. Dushani Pereira, Mr. Gihan Senaviratne, and Mr. Prabhas Kumar Singh. So we'll start with the introduction. So you see that traffic congestion everywhere in the world. So this will lead to wastage of money, wastage of fuel, and air pollution, sound pollution, and many other things. And we often see that some emergency vehicles are stuck in the middle of the traffic. And also we see that everyone is waiting and nobody is passing through junction. So things like that, right? And then why is this happening? So this is obviously the increase the number of vehicles on the road. Explicitly program traffic light control also, because these traffic light controls are explicitly programmed, so they are not taking the real-time information into consideration when making a decision. So we cannot solve the first one, but we can try to solve the second one and third one. Obviously there are many other reasons for that, but we can try to at least make this intelligent traffic light control. So we have identified 3 research questions. First one is, does the standard deviation of vehicle waiting time, considering the standard deviation of vehicle waiting time, has a significant impact on intelligent traffic light control? So we will come to this standard deviation of vehicle waiting time part in the later part of the presentation. But just to mention, this first one is, this is the first research question of us. And the second research question is, does the consideration of vehicle type can provide the emergency facilitation? So that is the second research question of this research. So since this is reinforcement learning based research, so we'll have a basic understanding on reinforcement learning. So reinforcement learning is an agent acting in an environment in order to maximize the given reward. So there's an agent and there's an environment. So what the agent do is, agent perform an action, right? Perform an action in an environment, then according to that action, the environment will be changed from state 1 to state 2. And from that state 2, agent will be rewarded. So then the agent will be rewarded with a reward. So then that from that reward, agent will learn to get better rewards. Okay, like agents will see, like if I do this action in this state, I have received this reward. And then agent will learn that to maximize the given reward. So that's the basic idea of reinforcement learning, to give a basic idea. So next we move on to the main components of reinforcement learning. So these are the main components of reinforcement learning: states, actions, reward. Of course, there's an environment. So if we map these components to intelligent traffic light control domain, so we can take environment as a traffic junction. So of course, in environment, we have vehicles and the traffic light. And states is the representation of traffic in a numerical way. So we have this environment, we have this agent. So agent, of course, the agent is the traffic light. So what the agent do is perform an action, which means he change the signal combination, the signal phase. So when the signal phase is changed, the vehicle will move and perform a new state. And then with that new state, the agent will be rewarded with a reward. And from that reward, agent will be learning how to control traffic better. And that's the mapping to our domain. So then we will move on to the related work quickly. So this is how the previous researchers have addressed the state representation in a reinforcement learning agent in intelligent traffic light control. So they have used queue length, waiting time, position of vehicles, and speed. So queue length, like how many number of vehicles are there in a queue. So, and these are the action representation. Set the current phase duration, set the cycle base ratio, keep or change the current phase, choose the next phase. So the phase that we are referring to is a combination of traffic signals. Like if we are, if we are allowing some direction green and some direction red, that is a combination of traffic signals, and then that is a phase. So we can move from one phase to another. So the other lane will be green, other lane will be red in the next phase. So these are the actions that the previous researchers has used. And also these are the rewarding criteria that previous researchers has used. So the queue length, waiting time, number of stops, throughput. So of course, researchers can use combination of these parameters to reward the agent. So we found a research gap in here. So the first research gap is no emergency facilitation is provided with intelligent traffic light control. And also in some cases, the states and rewards used in previous studies can mislead the agent. So if we consider these two examples, so first one is, and Chu and others in 2019 considered the maximum waiting time and the queue length as the reward, which can mislead the agent in following case. Like in here, if we consider these two, we have for state 1 and state 2, we have 4 vehicles in all of these states. And also if we consider the maximum waiting time, it is 30. From this one is also it's 30. So agent will be able to distinguish these two states, because he will get the information as, okay, maximum waiting time is 30, queue length is 4. So he will not be able to distinguish these two states, and also the rewards. And there is another example like this. The Wei and others in 2018 has considered the average waiting time and queue length as a report. So in this example, the average waiting time is also fails to distinguish these two states. So in here we have four vehicles. Okay, then the length is 4, and also the average waiting time is also 30. But in here, this vehicle waited 54 seconds, but all of these vehicles are just arrived. So this step is better than this one. So because this one is bad because it waited for 54 seconds, but this state, they have only waited for 15 seconds. So although this state is better than the first one, and the second one is better than the first one, the agent will not be rewarded correctly, or agent will be not receive the correct state to distinguish this. So for that, what we are using is minimizing the standard deviation of that distribution. So minimizing the standard deviation of vehicle waiting time can make sure that every vehicle will stay close to the mean. So that's our first research question, that we are applying, employing the standard deviation of the distribution as well. So so let me move to the design of our research. So we have used a simulation environment called SUMO. It is a simulation of urban mobility, which we can use to simulate a traffic junction. So this is the state design that we are using in our research. So we considered the vehicles within 100 meters radius and represent using M and P matrices. So if we consider this example, so this is the traffic. Okay. Yeah, this is the traffic environment. So in this traffic environment, we have these are the incoming lanes and these are the outgoing lanes, and these numbers represent the vehicle waiting times, right? So what we do is we map each lane to each row in the matrix M, right? So in this lane we have two vehicles, 10 and 20. So because we have two, this column represents the number of vehicles in that particular lane. So we have two vehicles, and this represents the average waiting time of 10 and 20. And this is the key of our research. It has the standard deviation of that distribution. So standard deviation of this. And also this is the waiting time of the emergency vehicles. So since there is no emergency vehicle, there is 0. Since this one contains the emergency vehicle, the waiting time is 5. And this is the congestion level of the outgoing lane. So the corresponding outgoing lane is this one. And also we inject matrix P along with matrix M. Matrix P represents the phase index of the traffic light. So we have defined 8 phases in the traffic light. So this is the one-hot encoded vector of the traffic light. So this hypothesis under this is that agent will have some understanding of the moving vehicles with the phase. So phase that I have explained before, that phase is a combination of traffic signals. So this is the action. So after action representation, so after 12 seconds, agent selects next traffic state. After 12 seconds, agent observes the environment and it will take the next traffic phase for the next 12 seconds. So this is the reward design. So we have K and Z hyperparameters here. So this is how we have defined the reward. So we have regular vehicle waiting time and regular vehicle standard deviation of regular vehicle waiting time times K, and it is subtracted with 15. And so we have another hyperparameter to control the impact of emergency vehicle. So this parameter is to control the impact of standard deviation to the reward. So that's the reward function that we are using in our research. So this is the deep neural network design that we are using. We are injecting matrix M from this direction, and we are injecting matrix P from this direction, and finally we do concatenation, and we have a fully connected layer at the end. So this is a deep neural network in the reinforcement learning agent. So this is how we learn. The policy learning is powered with fixed Q targets and double Q learning. So this is basically reinforcement learning stuff, and this is the high-level architecture of our research agent actually. So let's move on to training evaluation. So this is the evaluation plan of us. So we basically have two ways. Two ways means which we are testing with synthetic datasets, and we are training with synthetic dataset, and we are testing with real-world dataset. So for the training, we first should evaluate with the different case and get the optimal values for case and Zs, right? For that, we need to have different combinations and train. And then we, from that, we can take K and Z, best K and Z, and evaluate the proposed method with average only method, and evaluate the proposed method with fixed time and statistical methods. So I want to highlight this average only method. The average only method is same as the proposed method. Only thing is that if we go to this matrix, we have this column of standard deviation. So only difference in average only method is we have removed this standard deviation column from the average only method, where it will not contain any average only and any standard deviation details in the state representation. Also, we have removed this standard deviation from the reward for the average only method as well. So then we made some different combinations for K and Z. So especially we have Z equals 0, which implies no priority to the emergency vehicles. So we have trained with these configurations, and this is how we look. So if we consider the regular vehicle waiting time history, so if we zoom in the last part, you can see that K equals 0.5 and Z equals 1 has performed better than the other one. So for the emergency vehicles as well, so you can see that Z equals 0 is not performing well, right? It's going haywire. So if you zoom in, that you can see that K equals 0.5 is performing better than the other ones. So from that, so this is the summary. So from that, we take K equals 0.5 and Z equal 1 as to for the further evaluations. So so this is training evaluation with synthetic data set. So you can see that so this is the proposed method, the red one. So it is performing better than slightly better than the other ones. So this is the average only method by green. So this is the graph of standard deviation, and this is the training reward history. So you can see that proposed method was able to get higher reward than the average only method. The red one is the proposed method. So then the testing evaluation with real world data set. So unfortunately, the real world data set, we couldn't find a real world data set with the emergency vehicles, but we have other data. So we have tested with that. So we can see that so proposed method also performing for that real world data set as well, better than the other methods. So you can see that red one is the proposed method. It was able to minimize the regular vehicle waiting time and the standard deviation of vehicle waiting time as well. So this is the summary that the proposed method outperformed each and every other method. So these orange ones are the occasions where the other methods outperform the proposed method. But except those two cases, all the other cases, the proposed method was able to outperform the others. So for the conclusion, thus the standard deviation of vehicle waiting time considering has a significant impact on traffic light communication control, yes, because we see in the details. And for the second research question, so does the consideration of vehicle waiting time provide emergency facilitation? Yes, we see that in K equals 0, the emergency vehicle waiting time goes haywire. So obviously, we were able to minimize the traffic emergency vehicle waiting time approximately 0 using the vehicle type. So we will use a quick demo to this. So this is how our agent will look in action.
Yeah, say actually your
so you can see
is,
that
exceeded.
So there is an emergency vehicle as well. If we try to move that, you can see that okay, so it will pass quickly. So you can see that it will prioritize the emergency vehicles, and also you can see that they are controlling the traffic, how the agent is controlling the traffic.
So Harshni, say your time is has exceeded. Okay, thanks.
Yeah, sorry for taking more time.
Thanks, Lulmina. So now it is open for questions.
So have you tested with Toronto dataset? That link is not working. I just checked.
The link provided in the presentation.
I mean the dataset. I just want to check your dataset. It is not working. The link provided in the correct one, no?
Yeah. I think the link is broken, I guess. So we used that link before 1 year. So I think that will be broken. So if you want, I can provide the dataset I have it in my machine. So it's extracted from the Toronto, yeah, in Canada. So it didn't contain any emergency vehicle details. So we have to map that data set into the Sumo simulation environment. So we did some transformation of that CSV dataset to the XML network side. Sumo uses a XML network, so we should be written in XML, and there is a syntax for that. So we need to transform that dataset into the Sumo supported XML network. So
I have a small question. Generally, average go hand in hand with the standard deviation, right? So normally, when we tell something the average, so say statisticians, so they will always tell the standard deviation. But say, what made the others say not to consider the standard deviation yeah, for their research?
yeah, that was the question actually. So they have, in the previous researchers, they have tried many ways, like they have tried position of vehicles, speed of vehicles, average journey time, queue length, and many other parameters. But I have the question as well, because why they didn't use that standard deviation into the consideration. So anyway, they have used some combination of parameters to represent the states. But the main research gap that we identify is those every method will fail in some examples like that I have mentioned. So that's why we identify the gap there.
Okay. So I think I have to read the paper to fully understand the evaluation. So, but I noticed that there is kind of a wave pattern in the graphs you have produced.
Yeah. So that is because we
timestamp, right? The timestamp, there's say peak, and then there's a drop, and then there's a peak.
Yeah, that information I could not include in this presentation because it takes time to explain. So the thing is that the traffic distribution is according to some distribution called Poisson distribution. So it's kind of increasing in a way, and there are some peak traffic covers and low traffic covers and things like that. So that's the Sumo generates vehicles according to that. So anyway, there are some peak traffic covers, so the reward will be lesser, and anyway the average loading time will be more higher than the vehicles where the vehicles are in low conditions. So that's why there are curves like patterns in the graphs. Yeah, that's the Poisson distribution is the standard way that we test for the this kind of traffic controls.
Okay, thanks. Any other questions?
So you generated the dataset from a Sumo simulator, and you included the average as an additional parameter and
standard deviation actually additional parameter. I'm not sure what you are telling about.
No, I mean standard deviation. You calculated, generated the dataset, or the dataset itself generated all the required details?
No, when training, there is no data set actually. So this is a simulation environment for the reinforcement learning agent. So for the training, there is no data set. That's how the Sumo generates the vehicles actually. That is actually the data set, that how the Sumo generates the vehicle to the junction, traffic junction. And from that junction, the agent observes. So that is the kind of a data set for the agent. But there is no direct data set for the training. But for the testing, we used a Toronto data set, so which is also in CSV format that is not supported with the Sumo. So we need to transform that data set to the Sumo, because Sumo works in a different way. So it's use a XML format, like it's use some kind of network structure to generate the vehicles.
Hi, Chamindra Anusingh. Just to add to Aruna's question, I think it is you are using reinforcement learning So
Yeah.
there's no bootstrapping, there's no supervised learning initially, there's no training
No.
data set. So
No.
it basically over a period of time it adapts, it reinforces itself and it learns. So initially there's no learning, and but
Yeah.
as time goes by, it learns and adapts and reinforces
Yeah.
it. Right. Okay.
Yeah, that's the graph going from high to low when we are training. So
Right.
initially the average waiting time and things are higher, and also the reward is lesser. And
Yeah.
with the time that we learn, so that's why the graph, the behavior of the graph.
Right. If I miss something, you have compared the standard deviation. Is there a comparison with the same model with the mean or the average?
So at for the average only method, we have only removed that. If you remember that there is a column that we in the metric same, the standard deviation.
Right.
So we have removed that column from the average only method, and also there are some parameters in the reward function using standard deviation. So we have removed that one as well to remove the standard deviation information to the average only method. So from that we compare our proposed method with that average only method. So average only, the proposed method performing better than the average only method, as you see in the graph and the summary.
Right. Thanks. Got it. Yeah.
Okay. Thanks. So we can move to the next one. So the next one, paper number 103, suspicious human crowd behavior detection, a transfer learning approach. This is going to be presented by Mr. Peshala Liyanage. He's an undergraduate of the Information Institute of Technology, Sri Lanka. So he follows a BSc honors degree in computer science, and he is interested in deep learning and computer vision research areas. Okay, so over to Mr. Peshala Liyanage.
Hello everyone, I am Peshala Liyanage from Informatics Institute of Technology, Sri Lanka, which is affiliated with University of Westminster, United Kingdom. And I'll be presenting our research project, a transfer learning approach for suspicious human crowd behavior detection. This research was conducted under the guidance of Mr. Kumudu Fernando. This is the agenda of the presentation. Let's begin the presentation with the background of the research. Mainly suspicious behavior detection systems are used in the video surveillance systems. Purpose of those systems is to monitor the surrounding environment. Previously, those systems were monitored by humans by looking at multiple monitor screens that are connected with CCTV cameras. With the increase of the usage of these systems, the manual method was not practical to continue due to the natural human conditions like inattention and fatigue. Because of that, researchers have tended to research automating these systems. To be able to detect human behaviors in outdoor environments, these systems should be trained by using realistic video datasets that have been recorded in that kind of environments. For instance, the CCTV footages. But finding that kind of datasets is a hard task in this research domain. Some of the problems are mentioned here. Those are lack of realistic video datasets. Some suitable datasets include less number of video clips. The available large datasets include untrimmed and unannotated video clips. Because of that, researchers have to create datasets by themselves, or they have to perform costly and time-consuming data pre-processing tasks. Those reasons are negatively impact for the improvement of this research domain. These are some of the challenges that researchers have to face in this research domain. Most of them are related to the different illumination conditions and environment variations. These are some of the existing research projects that can be found in the literature. Most of them have mentioned the dataset limitations and the impact of those limitations on their projects. The identified gap of this research is a proposed solution that addresses the dataset limitations in this domain has not been proposed yet. And this is the aim of this project. When it comes to the scope, as a POC, only a human violent behavior detection system has been implemented. This is the flow diagram of the system. First, input a video to the system, then frame extraction, high-level feature extraction, feature mapping, classification, and finally the detected event is shown to the user. This is the high-level architecture of the system. This is the model architecture of the system. The transfer learning approach is used for this. After performing lots of experiments with MobileNet, VG16, Inception version 3, and the ResNet 50, the MobileNet was selected as the perfect model for this approach. The MobileNet is used to extract the high-level features from the frames. This model is mapped using a time-distributed layer to maintain the sequence of features parallelly to prevent feature mixing with each other features. This model needs a batch of 30 frames to identify one behavior pattern. A LSTM layer is used to map features of those 30 frames. It can map feature variations against the time. These feature maps are fed to the decision layer of the model and it has 3 polyconnected layers. These are the technologies that have been used to implement the system. Violent flows is a small dataset that includes unannotated video clips. Considering these factors and the aim of the project, violent flows were selected for this project. Let's move to a small demonstration of the implemented system. This is the implemented suspicious human crowd behavior detection system. It has a simple GUI to perform the basic functionalities. Only publicly available video clips are used for this testing purpose. First, I selected a video clip that includes human crowd violent behaviors. It is detected as a violent video. In this video, it also includes the human violent behavior and it is accurately detected. In this video, in the very first seconds, it doesn't include any violent behaviors. And you can see the illumination condition in there. First, it detects as a normal video. After sometimes there is a violent behavior happening and it is accurately detected. In this video, in the first seconds, it doesn't have any violent behavior, but after that, it has some violent behavior and it is detected as a violent video with accurate confidence. In this video, you can see there is also violent behavior and it is detected with high confidence. Now I have selected the normal video because this is also crowd video, but it doesn't include any violent behaviors. As you can see, it doesn't include any violent behaviors, but there are people who wave their hands. They are waving their hands very fast. It's also similar to some violent behaviors, but it's not a violent behavior, but it has some waving hands, fast waving hands. The model is capable of identifying that this is not a violent behavior and it detected as a normal video with high confidence.
Dulmina, you can say stop the demonstration and go with the paper.
This is not a violent video. They are celebrating their victory after some tournament. It looks like a violent video, but the system can accurately detect it as a normal video with high confidence. This is a normal video. It includes Indo-human activities and the system can detect it as a normal video with high confidence.
Yeah, Dulmina, you can continue with the discussion on the paper. Says you can stop the demonstration.
This video includes few human interactions. Even though this video doesn't include sufficient human interaction, the model is capable of classifying this as a normal video accurately. This video includes some sport activities. There are no any violent behaviors, but there are human interactions happening there, and the model is capable of identifying this as a normal video with high confidence. In this video, the people are running and it is detected as a normal video. This video is also a normal video and it includes walking people, and the model is capable of detecting it as a normal video with high confidence. This is again a violent video and the model is able to detect it as a violent video with high confidence. And all processed videos are saved in this output folder and we can play back those videos again. And also there is another Excel file. There are some numbers saved in this file. Actually, those are the seconds where the suspicious activity happened in the video. So we can identify where the suspicious activity happens inside the video using this system. Okay, then let's go back to the presentation. These are the tests that were performed, and the red colored ones are unique to this research. 98 video clips have been used to test the system, and only publicly available videos have been used for this. Because of that, the project doesn't have any social, legal, or ethical issues. 32 models with different configurations have been tested to identify the best performing model architecture for suspicious behavior detection systems. The tested factors are the transfer learning model, number of trainable layers of that model, number of LSTM neurons, number of LSTM layers, number of hidden layers, optimizer, and the impact of the augmentation. The accuracy, precision, recall, and F1 score were calculated. These are the configurations of each model that gave best results. The Model 6 and 29 were selected for further tests. Even though the VGD16 version shows good accuracy, it cannot be tested in the local machine due to the GPU memory limitations. This is the confusion matrix of the Model 6, which is the mobile net version. The Model 6 and the Model 29, which are mobile net and ResNet 50 versions, are tested with these 8 different scenarios. Both of these models have been trained using only crowd violent and crowd normal videos. Both models were able to detect violent behaviors in those similar scenarios, but the Model 6, which is the mobile net version, was able to classify other scenarios as well better than compared to the ResNet 50 version. Considering that, the mobile net version was selected as the best model to implement suspicious behavior detection systems. These are the research projects that are more similar to our project. The highlighted projects have used similar approaches to ours, or they have used the same dataset that we use. As you can see, except this project, all the other projects have fewer values compared to our project. This project has used a transfer learning approach with Inception version 3 and LSTM, but they have manually trimmed and annotated a large-scale dataset for their project. Because of that, we recreated their approach according to our architecture and performed the previously mentioned tests. These are the test results of Inception version 3 models. As you can see, all the models gave low accuracies compared to the other models. So it was concluded that the Inception version 3 is not the perfect model to implement suspicious behavior detection system using our approach. This is the performance test results of the Model 6. It took only 0.3 seconds to do one prediction using 30 frames. And because of that, we can assume that this model can be used to perform real-time processes. These are the contributions of this research. A novel model architecture was proposed by combining the mobile net and the LSTM, and a small dataset that includes realistic video clips is sufficient to train this model, and it's not needed to use a large-scale dataset to train this model. So it's a solution to the dataset limitations in this research domain. And the model has been tested in different scenarios, and 4 state-of-the-art models have been tested and identified their detection capabilities when it comes to this research domain. And a human crowd violent behavior detection system that works well in the outdoor environments was implemented. These are some limitations and future work of this research. This research project was presented to some machine learning experts, and the feedback they have given are mentioned here. This is the conclusion of this research project. Thank you.
Thank you, Dulmina. So now this work is open for discussion. Sorry, Vishal.
Hi, Veshala, Chamindran Singh. Just to, if you can just explain a little bit about the feature extraction part altogether from the videos, from the frames. What were the markers that you used?
Actually, for that, I used the transfer learning approach. For the feature extraction, I used the mobile net module, and I trained it using our dataset, which is our info dataset. For train that feature extraction model, I froze some layers and train 9 layers with our dataset. Then I can use their already learned knowledge, already learned weights to our project. And to identify that feature extraction model, the best feature extraction model, I tested 4 different models that I mentioned in the presentation. Those are MobileNet PGV16, ResNet 50, and Inception version 3. So basically, I use that for the feature extraction. It provides the high-level features like it can detect kind of object level. Yeah.
So the sequence of the frames and the because each frame is extracted, and the sequence of the frame would have had a kind of a impact on that learning.
Yeah, we need to maintain the. For example, I provide 30 frames at once to the model. The detection, it detect one behavior using 30 frames inside the video. So we need to provide 30 frames at once, and the 30 frames should be processed parallelly. So we need to maintain that 30 frame, the features of 30 frames parallel to, and we should provide that parallel to the LSTM layer as well. So to maintain those parallelly, I wrap that feature extraction model using a time distributed layer provided by Keras. Yeah.
Right. Okay. Right. Thanks.
Sorry, you are on mute.
I have noticed that say the accuracy for the 2% violence was low. Yeah. Could there be any explanation for that?
Actually, I trained the system using only crowd violence videos. those with the training dataset include crowd violent videos. So, but I tested our output of final model with different kind of scenarios. For example, 2% and there are less person interactions and this kind of videos. But unfortunately, it provides low accuracies when it comes to 2% violent videos.
Okay. So any other questions from the audience? Okay, so thank you, Peshara, and thanks for the audience for waiting. So be with us for this. Yeah, more than 2 hours. Thanks for Aruna and Chaminda for your intuitive questions. And I thank again the presenters for sharing their research work with us, and the organizers for allowing me to share this session. Okay, so thank you again, and hope to meet you again in the next ICTR 2022. Thank you.
Thank you very much, Session Chair Dr. Andrew Charles, for leading this session, and the authors who have presented their papers, and all the other participants. Now we can move on to the next item in our agenda. Next, we have is a technical session on unlocking national innovation through industry-academia collaboration, powered by Dialogue 5G Innovation Center and Innovation Foundry. I invite all of you to join it in the main session of this meeting. That concludes session 1B of ICTR 2021. Thank you all very much.
Yeah, thank you, Kavindya and Ashoda, for your assistance. Thanks.